Okay, general relativity step by step. Last time I was talking about the Jacobian matrix here, which is this nice matrix of partial differentials. And the example I chose was Cartesian going to polar coordinates. So x and y, and we're given x and y and we wanted r and theta. And that's the little picture there. And we've figured out the Jacobian matrix here. And it comes out to be this. And I worked it out in 3 or 4 different ways, some of which had just x's and y's in, and some of them had just r's and thetas in. What I'm going to do now is the inverse Jacobian. What I've got here is, instead of x and y known, going to r and theta, I'm going to go the other way. R and theta goes to x and y. Very simple relationship, so it never hurts to draw it. And of course x equals r cos theta and y equals r sine theta. So straight away we get x squared plus y squared equals r squared sine squared plus cos squared, which equals r squared, so we're on the same page. Okay, so let's form the Jacobian here. What's the Jacobian of the inverse transformation? Well, it doesn't hurt to write it out. Now last time we had, where is it? There it is. Di r, di x, di r, di y, di r. So we had the r's on the top and the x's and y's on the bottom. Now I'm going to do it the other way around. I'm going to have the x's and y's on the top. Pinch in a bit. X di r di x di theta di y di r di y di theta. But now we've got these two relationships, the forward relationship, so all I do is differentiate these two things here. Equals di x di r is just cos theta. Di x di theta is just r. Differential of cos is minus sine theta. Di y di r is just sine theta. And di y di theta, di y di theta is going to be r cos theta. There we go, isn't that beautiful? Beautiful. So we've got this thing, and of course I could express the cosines and sines in terms of x's and y's, but I can't really be bothered to do that. I think this is a nice way to do it. What I'm going to ask is, I'm going to call that JR for reverse, JRev maybe, and this one here that I did last time, this is going to be, I just wrote down J. I'll just pinch in a bit. I'm just going to write, that's going to be J forward. So what I'm going to ask is, what is the matrix product of J forward and J rev? Well, let me just write it out symbolically and then I'll show you that it works. Of course, J forwards matrix multiplication J rev should equal the identity. Should. Because a forward times the reverse, if you go somewhere and then come back again, you've sort of come back to where you started. So it should be equal to the identity matrix, like that. But what I'm going to do is actually do it a little bit more carefully than that. I'm just going to write it out. The forward one had the r's on the top and the x's and y's on the bottom. And then the reverse transformation was up here, which had the x's on the top and the r's and thetas on the bottom. Di x, di r, di x, di theta, di y, di r, di y, di theta. Now, at this point, you might be saying, well, hang on a minute, can't we just substitute in? But I'm doing the general case. What I like to do is to have a mixture of the general case and then the specific example, and we flick backwards and forwards between the specific example and the general case. So I've got four components here. I've got blom, 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 and I'm just going to call these, oops, I meant to erase those. I'm going to call these A, B, C, D. A equals, what does that equal? Well, that's the top row with the left column. So it's die R, die X, die X, die R, plus, so that's that times that. This one here is die R, die Y, die Y, die R. B equals, I'm going to have to scrunch these up because I want to get it all on the same line. I'll just do that. B equals, it's the top right element, so it's the top row with the right row. So it's die R, die X, die X, die theta, plus die R, die Y, die Y, die theta. So it's that term with this term. C equals, I'm not going to fit it all on, am I? Oh, yes, I'm going to fit it all on. C equals lower left element, so it's the low row with the left element. So it's die theta, die X, die X, die R, plus die theta, die Y, die Y, die R. And D, lower right, so it's die theta, die X, low right, die X, die R, plus die theta, die X, die Y, die theta, die theta, die X, die Y, die theta. Right. So what's A equal to? Well, by screencast number 1, this is a partial derivative. And look, we've got die R, die R, die R, die R there. So basically we have got, effectively we've got die R by die R, which equals 1. There's a hell of a lot going on there. What we've done is we've just observed that we've got a total differential of R with respect to itself. It's delta R over delta R because it's just 1. That's A. What's B equal to? Well, that's die R by die theta by the same argument, because we've got, well, it's a delta R over a delta theta, because we've got a delta theta, which is equal to 0. It's a partial differential. It's a partial differential, die theta, which equals 0, because these two guys, R and theta, can be varied independently. They don't have a functional relationship. C equals, what equals die theta, die R, which equals 0, and D equals die theta by die theta, which equals 1. And so we can see that this matrix here, J forwards, matrix multiplication J reverse, equals 1, 0, 0, 1, which equals the identity. Beautiful little thing. Beautiful, 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 beautiful little thing. Well, it's one thing to see that in the abstract. It's quite another thing to actually multiply the two things out and see if they actually do what we want them to do. So let's try that. There's reverse, and what was the forward matrix? I forgot. No, here it is. Cos theta. I'm going to pinch in a little bit here. So there's my forward matrix. Actually, I'll come in here. There's my forward matrix. Yeah. Cos, sine, minus sine over arc. Cos, sine, forgotten it already, minus sine theta over r, cos theta over r, minus sine theta and cos theta over r. Incidentally, while I'm doing this, I should have set out the determinant, and the determinant is pretty obviously 1 over r, times cos minus r sine theta, oh, I'm not going to remember that, cos minus r sine theta, cos theta minus r sine theta, just copying off here, sine theta r cos theta, here we go, that's better, equals, a nice big matrix. Well, let me write it down. It's going to be equal to matrix A, B, C, D. A equals cos squared of theta plus sine squared theta equals 1. B equals minus sine theta over r times cos theta plus cos theta over r times sine theta equals 0. C equals pretty much the same thing. No, that was, yeah, C is low right, which is 0. And D equals 1, of course, because it's 1 over. Well, actually, I'll write it down explicitly. D equals minus sine squared theta times r over r, which of course cancels out if r is not equal to 0. Sorry, that's a plus, because 2 minuses make a plus. Plus cos squared theta times r over r equals sine squared theta plus cos squared theta times r over r equals 1 if r is not equal to 0. And of course, if r equals 0, it's very difficult, because it's a singular point. So our little matrix there is 1, 0, 0, 1, and we've shown that the forward Jacobian times the reverse matrix multiplication with the reverse matrix is equal to the identity matrix. And this works however big your matrix is. I mean, I could have a Jacobian which is die f, die x, die f, die y, die f, die z, Jacobian, and we could have dg, dx, dg, dy, dg, dz, and this one will be d8, let's say, but dx, di-h, dy, di-h, di-z. Observe, you need a square matrix. Need a square, just pinch in a little bit, need a square matrix. Why do you need a square matrix? Well, you need a square matrix because you're mapping a vector of 3, in this case, length 3, to another vector of length 3. It's because you need to invert it. You need to invert J. And invert J can mean two things. It can be inverted in a matrix sense, to work out the matrix inverse. Or it could mean calculating the backward transform, like we calculated Cartesian to polars, and then we calculated polars to Cartesians. So there's just some simple examples of the Jacobian matrix for polar to rectangular coordinates and back again. Next I'm going to do a slightly more complicated example, and you'll see why when I start talking about basis functions and fundamental tensors. Okay, I'm going to stop there.